So on to this morning. Our speaker this morning is Professor James Clark from York University. James is a lecturer, scientist and entrepreneur. He's a university professor in England, company chairperson in Ireland, and a public speaker everywhere. His mission is to use the circular economy driven by green chemistry to change our perception of waste. His work takes him all over the world, from shanty towns in South Africa to waste companies in China, and from classrooms in India to orange farms in Brazil, and now the Orkney Isles. James is going to tell us that green chemistry seeks ways to transform waste or renewable natural materials and make safe chemicals and recyclable products. He might even tell us how you make clothes from pineapple leaves. Anyway, enough from me. James, over to you.
Good morning, and thank you very much for the opportunity to be here today. My first trip to Orkney. I think it's about the most northerly place I've been to in terms of giving a talk. So I can feel the air, feels nice and clean. It's lovely. So anyway, I'm going to talk about chemistry, yes, but not so much on the chemical side, not so much on the molecule side, more to do with the kind of underpinning, what it means to us, society, what it means to us in terms of going forward in the context of what people now refer to as the circular economy. I'll try and explain a bit about that a bit later. But the most important slide really is my first slide here, which is the kind of as in everything slide. So this is meant to show that, whatever you are wearing, sitting on, came here in, will eat afterwards, etc., will be made from chemicals. And maybe people don't think about that so much. Maybe they should think more and might help give chemistry and chemicals a better name. But the reality is everything here is dependent upon chemicals. Now, I could give a talk, and other people do, which just focuses on that and basically pushes the fact that chemicals, chemistry underpins everything. And each of those items I've got there is a story in its own right. My angle on this is a bit different. And when I first started talking about this, a long time ago, maybe 30 years ago, when I started talking about the problems behind the chemistry and the chemicals, I was not terribly popular with my fellow chemists, because they saw the positive side. I saw the opportunity to make things better. So in reality, what I'm going to talk about today is really how to make what's behind all those different articles better. So any one of those, pick any one of those at random. I mean, for example, cosmetics. So cosmetics, which are very popular especially among wealthier societies. They are very interesting, complex mixtures of lots of different chemicals. They provide various functions which are nice or in some cases beneficial and certainly are appreciated by us. Actually, within that, you've got maybe 10, 20, 30, 40 different chemicals in a typical cosmetic formulation. Each of those chemicals has been made from something, and the majority of those has been made from oil, from petroleum. And each of those chemicals is made using chemical processes to actually make the thing that goes into the mixture. And at the end of it all, when you wash the stuff off your face or whatever it is, it goes into the environment. That's the life cycle of a typical chemical going into any of these articles. Now, that may not be so bad for cosmetic chemicals, or maybe it is. It depends on the chemical. In other cases, however, it might be more of a concern. Like, for example, with electrical devices, we have batteries. And batteries are full of, in some cases, quite hazardous, quite nasty chemicals you don't want to be wandering loose in the environment. Now, what's of course happened, and what we now appreciate more and more, is that many of those chemicals in these various articles are getting out into the environment and maybe cause a problem. I mean, one of the recent examples are microplastics. People get very worried now about microplastics, probably correctly so. Microplastics are coming from plastics, and plastics are coming from a lot of those articles, if not all of them, contain plastics. I'll talk more about plastics a bit later, but actually, in reality, think about it now, because plastics are, what you're wearing, you may not realize this, but what you're wearing almost certainly contains plastics. What you're sitting on certainly does. The building infrastructure contains plastics. The cars you may have come here on contain plastics. The airplane I flew in yesterday contains plastics. And many of those plastics are really good because they, for example, make your aircraft lighter weight, therefore it uses less fuel, etc., etc. Other plastics, like the packaging, I'll talk a bit about later, maybe not so good, maybe not so necessary. The problem is most of those plastics get in the environment and they break down, creating microplastics, etc., etc. So what I'm trying to say is I could tell a story about all of these different articles of society, and every one of them presents, I would say, more opportunities than threats, to make things better, to make things greener and more sustainable. We want the benefits. We want to be able to use the plastics for the good things. We want to be able to use the cosmetics to feel nice. We want to be able to use the pharmaceuticals for obvious reasons. We want to be able to drive the car to eat our food, etc., etc. Lots of wind turbines around here as well. Really interesting, complex examples of chemicals. And let me use that as an excuse to move to my next slide, which is really showing, where we are now, because all those things I showed before contain chemicals. They all come from somewhere, as I said before, mostly oil. Nowadays, we've moved towards a whole bunch of new things. We are making things even more complicated by building more devices. And the driver behind this particular set of examples I've got here is good. It's to try and move towards a low carbon economy. Oh, that's an interesting topic. I could talk for hours just about that. Low carbon. So nowadays, if I talk to a politician, for example, they get low carbon. They think they do anyway. They think low carbon's good. Low carbon's good because it means, therefore, probably less carbon escaping again into the environment, in this case, in the form of CO2 or methane or other small volatile carbon molecules, which are causing environmental problems, such as global warming. Absolutely. Very important we reduce that. Therefore, they sort of trace back, where's the carbon coming from? It's coming from burning fossil fuels. Absolutely. That's a real issue. Another example of oil, petroleum dominating our societies and has done for the last 200 years. Therefore, we build new things. We build electric cars. I drive an electric car. I'm delighted with it. I'm very proud of it. I mentioned the wind turbines. You've also got things like solar, of course, which is fantastic, as a source of energy. And places I go to, for example, in hotter climates like Africa and so on, have a huge potential to use solar more and more as their source of energy. The interesting thing from a chemical point of view is that all of a sudden we're now using new chemicals. These things here, dysprosium, neodymium, praseodymium, I'd never heard of them. I'm a chemist. I've been a chemist all my career. They're obscure elements in the periodic table. And suddenly they become really popular and very important because of these new devices. Is that a problem? Well, I would suggest it could be because we don't do it in a thinking way. We just rush into the area without thinking about it, for example, electric cars, which I believe in. I'm very strongly supportive of electric cars. But if we electrify the entire transport fleet in the world, we don't have enough metals. Full stop. We can't do it. Based on our present technology, we cannot do it. But people are pushing on anyway without thinking about it. Well, at least think about it and try and work out what does that mean. Because in reality, lithium, everyone talks about lithium, very important element, present in most modern batteries, including electric cars. And there's a big worry about future lithium supply. A lot of it comes from places like Bolivia, for example. Fine, but there's a limited quantity there. We're now looking for lithium in Cornwall. All sorts of places are finding new sources of lithium. Why not actually think the more obvious answer, which is let's make sure we keep using the lithium forever? So at the end of life of a battery, I've got a battery around here in my kit, the battery is, what do we do with it? We might say we recycle it. We don't get the lithium back. We don't recycle the metals on the whole. We don't. Therefore, they are linear. It's a linear economy. And therefore, we have the problem of trying to always feed the beast. More and more lithium, dig more and more holes, etc., etc., etc. Crazy. This is starting to give you a hint, maybe, about why the circular economy is so important. The consequences in gross terms are volumes. Look at this. The amount of stuff. This is the amount of stuff we use now in society. And that's the value. Of course, we all say, politicians say, it's great, our GDP is going up. Isn't that fantastic? Is it? Really? What does that mean? If that means we're consuming more and more stuff, that is not a good thing at all. It doesn't make sense. It's not sustainable. So here we can see the mass demands going up and up and up. The carbon demands are starting to level off, we think. A lot of this is prediction. It could go down. So depending on the success of low carbon technologies, we may start using less and less carbon. That's good in the sense it should mean less and less carbon getting out into the environment in an uncontrolled way in the form typically of carbon dioxide. But if it means we're consuming other stuff, which maybe we can't get back again or don't get back again, is that so good? We have to be very careful about this. We can't just carry on consuming, and not putting anything back, except, of course, into landfill sites, because that's the real issue. The reality is, of course, we end up putting stuff into the landfill sites, we burn it, or we let it escape. That, by the way, is a picture, an infrared image of a plastic island off the west coast of the US. There's Japan. You get the idea of the size of these things? This is microplastic. We can't see it with our eyes, but it's there, just below the surface. The amount of plastic in the sea is staggering, absolutely staggering. And we've been pouring it in there without realizing about thinking about it. Just ridiculous. We can't carry on doing that. We're taking a limited resource in the form of oil, we're then consuming it in the form of plastics, and then dumping it in the environment in a way it will not break down. It'll stay there for hundreds of years. Crazy, crazy. Now, the motivation, the drivers behind all that, or the reasons why this is occurring, are not just us being very careless. Also, underpinning that is some of the chemistry I was talking about before. We have to remember the chemistry itself could be better. This gives you an idea about efficiencies of chemical processing. The right-hand side is basically a measure of waste. If you can imagine what it says, it's the ratio of waste to product in kilograms, no matter what it is, the scale is. Now, oil refining, funnily enough, people say it's bad, dirty, horrible. And personally, yes, I'm very much against it in terms of wanting to move away from it. But actually, it's a very, very efficient industry. We could learn a lot from oil refining and petrochemical manufacturing. There's hardly any waste. As you work your way through higher value chemicals, large volume chemicals like sulfuric acid, phenol, and so on, through fine chemicals, like, for example, the metals I talked about for batteries, into the pharmaceuticals and really high value stuff, the waste, the efficiency of the chemistry gets worse and worse. Pharmaceutical manufacturing typically makes well over 100 times more waste than product. They know that. I'm not saying they should stop making pharmaceuticals, quite the opposite, but they could make it a lot more efficient. To be fair, they have now. There is a green chemistry movement in among the big pharma industries. It could be better, it could be more strong, it could be quicker. But at least there's an awareness now they could do things better. So, we're using a lot of stuff which isn't renewable in the form of oil. We're carrying out chemical processes which are far from efficient and generating much more waste than product, and we're dumping everything at the end of its life without thinking about it. Now, what does that mean in terms of elemental availability? It means that we're running out. Here's a periodic table. I hope you recognize it. I'll have another one later on, just in case you've forgotten it. Look at the color code. What it means is the ones in red are now running out we reckon less than 50 years available. Look at those metals. What's here? There's some very interesting metals up here, like, gallium, germanium. This is the electronics industry, by the way. This is the precious metal industry and the catalysis industry. We're talking about entire industries dying unless we do something about this. Now, people sometimes say, well, hang on, you're not really saying there's only 50 years worth left of tin or indium. Indium's a good one, for example. Is that true? Well, yes and no. The Earth's capacity is huge. If you carry on digging a deep enough hole, you will find more. But, how far can you dig? I mean, the environmental, the energy cost, the economic cost of doing that gets crazy. We can't afford to do that. This is based on the easily available, what we know is there. Sure, if you want to carry on digging, you can find more. In the US of A, they have a society based on mining the asteroids. They have a serious plan there to mine asteroids. To me, that's like, I'm a very keen on astronomy, but hang on a second. I'm not sure that's so practical. That sounds a bit. Anyway, they're seriously talking about it. That's how crazy the whole thing's become. Why do that? It hasn't gone away, The only thing that escapes the environment that's relevant in terms of availability is helium. We are losing helium straight out into space. Everything else stays here. It stays here. The lithium doesn't disappear. It just goes in a hole in the ground. We can use it again. It's all about circularity. And it's also, as I said to you as well, also all about the chemistry. Don't forget the chemistry. I won't get into the chemistry much in this talk, but there's a whole world out there for green chemistry to tackle in terms of chemistry. And a lot of that's also not just underpinned by efficiency, but also underpinned by dangers. We still do chemistry in a very dangerous way. I'll just show one negative slide here, which reflects that, which is a very famous incident some of you may have heard of called the Union Carbide incident in Bhopal. And about 30 years ago, there was a chemical explosion in a place called Bhopal in the middle of India. And the reasons behind that are very educational in terms of how not to do chemical processing, because they were storing large quantities of a very dangerous volatile chemical very close to a high population zone. And one night, one of the tanks ruptured. A cloud of poisonous gas was driven over by the local winds over the population, and thousands of people died very quickly. Tens, if not hundreds of thousands of people have suffered ever since from blindness, from genetic abnormalities, from a whole series of horrible things, And this was all because the chemistry was done. The chemicals were handled in a very, very careless way. So there's so many places where we can do much, much better. And remember, underpinning all of this, we've got oil refining. And this is what we've chosen to base our society on. for the last 100 years. I mean, don't think oil's been there forever. It hasn't, you know? We haven't been using oil that long. Really, people look back, the 20th century was very much the petrochemical age. The 21st century, I hope, is becoming the era of transition, the century of transition, going away from petrochemicals towards more renewable chemicals, which I'll start talking about in a moment. But we have to be careful because, you know, this is a very efficient industry, as I said. The chemistry involved is sometimes very nasty and very dangerous. The chemical processing could be a lot better, but it's very efficient. And it makes everything, you know, the range of things, eliminating plastics through pharmaceuticals, through solvents, I'll talk briefly about later as well. Just about everything you can think of that contains chemicals comes from petroleum. Why? Because it's cheap and available. So 100 years ago, when they started discovering oil in large quantities, it was very easy for the chemical industry to say, oh, I'll have some of that. It's cheap, it's readily available. I can use it to make things. And they built the entire chemical industry around petrochemicals. And of course, also interestingly, the chemistry education system was also based on this thing as well. So most chemical education is still hydrocarbon based because that's where it started 100 years ago. Go back 200 years, it was a completely different game. Go forward 100 years, I hope it'll be different again. I imagine next you look, you can think this is a very short period where petrochemicals dominated. But the reality is, of course, it is running out. I mean, okay, like I said before, with metals, you can dig deeper holes. But look at where they've discovered oil recently. In places like, I mean, for example, Gulf of Mexico disaster 20 odd years ago. The Gulf of Mexico, I spoke to the chief BP engineer who was in charge of that project. And he said, if you're going to mine for oil in a place like that, a disaster will occur. It's such horrible hostile conditions to do that. Or, you know, the tar sands of Canada or wherever you look, you know, we are getting more oil by going to more and more difficult places, by digging deeper and deeper holes at higher cost environmentally and economically. We have to get ourselves off this. We have been very much weaned on, used to the idea of petrochemicals based on oil. We have to change that. What's the solution going forward? Well, I'm now going to argue about the use of biomass as a future source of chemicals, organic chemicals, certainly, replacing the petrochemical carbon. I don't say replace carbon, by the way, because we are carbon-based. Nature's carbon-based, and most of the things we make are carbon-based. Fine. It's where the carbon comes from and where it goes to afterwards. Biomass is nature's way of handling carbon. We are biomass. The trees out there are, not only trees in Orkney, the trees, wherever they are biomass. The plants are biomass. Seaweed, I'll mention briefly, is biomass. It's all biomass. Great source biomass. Anecdote, I was giving a similar talk to some Chinese people, quite a few years ago, some young students, and talking about biomass and saying, okay, in your country, what do you have as a good source of biomass? And one of them said flies. And I said, flies? I said, yeah, flies. And we talked about this. And one of the other students said, how do you capture the flies? And he said, Chinese flies are very obedient. They keep together. Okay, that's very nice. Somebody else said, rather more alarmingly, dead people. I said, well, it's true. Yeah, dead people are a source of biomass. I'm not just sure I'm so keen on the idea of a future chemical factory being based on dead people, but I suppose it's very efficient. But anyway, the point is biomass is there, and it's the basis of what we now refer to as the circular economy. I gave a similar talk to this about 14 years ago, almost exactly 14 years ago, at the British Association for the Advancement of Science in Bradford. And sitting in the audience at the time was a lady called Ella MacArthur, you may have heard of. And Ella MacArthur just recently got back from breaking the world record for sailing the world single-handed. And she was fascinated. She had left school at 16, no chemistry knowledge whatsoever. I gave this talk, a similar talk, and she thought, okay, this is interesting because living on a boat for a year, she learned about the circular economy without realizing it. She realized she couldn't afford any waste. Everything had to be used again and again and again. She was driven by this to the point she really drove, as much as anybody has, the whole European circular economy movement. Of course, Dame Ellen MacArthur now is world famous. Her circular economy activities are now very well known across the globe. The point is that even people without the education, without the background knowledge, can make a difference in this area. One of my brighter students came up with a nice sort of diagram to represent the difference between fossil carbon and between renewable carbon. So we can talk here about reusing, recycling, and also, of course, renewing. So renewing as in getting it back again, like, recovering from the atmosphere or wherever it is, and using it again. So we can talk here about, if we think about bio-based carbon can make things and should be reused as much as possible, recycled when you can't reuse it anymore, And also, ultimately, of course, everything ends up in the environment like us. And when it does go in the environment, let's make sure it's renewable. In other words, the environment recognizes it. The environment does not recognize polyethylene. It recognizes us and breaks us down in a very efficient way. Fossil carbon should be reused, it should be recycled as much as possible, but it can't be renewed. Fossil carbon takes millions and millions of years to be renewed by nature. It's not practical in a circularity sense. The rest of this, by the way, is just a whole bunch of policies and legislation and drivers of change and, lots of things which are all necessary. All this has to be underpinned by the right law, by the right policies, by the right encouragements, at all sorts of levels, personal level, industry level, society level, national levels, etc. EU is very good at this. To be fair, the European Union has been world leading at a lot of its policies. It's great at, by the way, writing policies. It's not so good at putting them into practice, which is another story. But anyway, at least something's happening. Now, one of the things buried in there talks about something like biomass sustainability. And so just because it's biomass, like dead flies or dead people, it doesn't mean to say it's sustainable. We have to be careful. So a good example of that, I would say, is around fake palm. Fake palm? It's like, well, palm oil is like, somebody said more than half the articles in every modern supermarket contain palm oil. It's incredible how palm oil has become key ingredient in so many different things. It's great from a chemist's point of view. It's a very nice product, readily available, quite low cost. Chemically, it's not too complicated. You can modify to make all sorts of different applications. So that's very nice. The problem is, of course, that people saw this as being a great money opportunity and therefore started to deforest areas to build more and more trees that grew made the right oil to make more and more palm oil. So palm oil now is huge. Even in the UK, we're talking about staggering amounts. I mean, 1 million tons a year just inside the UK. Worldwide, you can imagine the numbers are incredible. We need to be careful because although it's there, although it's renewable, although it's green in many senses, it does have some underpinning, some very serious concerns. And the ones that Greenpeace have been very active in pursuing are around the devastation of local habitats for example, orangutans. This is a bit out of date. I'm sure it's more than 5,000 a year. But the point is, a lot of animals are losing their natural habitat because we are deforesting to basically grow things that make us lots of money. So we have to be careful. So it's not just about being biomass, being natural, being renewable. We've got to be careful about what type of biomass we're talking about. My own personal favorites are using waste. Let's use waste. I'm going to talk about oranges next. Straws are also widely available. We don't, by the way, people say, oh, straws are used for feeding animals and bedding and stuff. The vast majority of straws in the world, cereal straws, are burned. They're still burned. And it's a terrible waste. It's also very damaging, of course, in terms of the environment with all the carbon dioxide. And don't forget could be flies. Flies are actually a very interesting source of chemicals, but also crustaceans, so crabs and seafood generally is an amazing source of raw materials for making all sorts of different chemicals. And there are more and more companies recognizing this, some in the UK, many more abroad. I went to the world's largest processor of seaweed, for example, which was in China a few years ago. So there's a lot of interesting things going on around utilizing resources which are natural, but which we don't really want ourselves to eat or to do anything else with, essentially. So we started to analyze this in terms of, so where is all this stuff, this biomass stuff, and how much is available? And we found that actually the numbers are pretty amazing. So a good excuse to travel around these different places as well. As you heard before, I spent some great time in Brazil, around orange farms and so on. Africa, what fabulous resources there. Asia generally. Europe is not, we don't grow as much as most other regions. We do process a lot though. So we generate lots of food waste by processing. Now, I'm not suggesting we turn food waste into chemicals if it can be used as food. Absolutely not. But the point is, we don't have to use the food edible waste. We can use all the inedible stuff, the shells, the stones, the pith, the peel of the orange I've got sitting there, etc., etc. And look at the numbers there. We reckon there's about 3 billion tons of inedible food supply chain waste. 3 billion tons. I'll put that in context. The entire chemical industry, making plastics, making pharmaceuticals, making solvents, making everything I mentioned before, is about 1 billion tons of carbon. This is more than we need just to make all the chemicals. If you start making fuels as well, as people have been doing, it gets a bit more complicated in terms of the maths, but still, it's interesting. So very interesting. And the resources are amazing. I mean, Brazil, almost 400 million tons a year sugarcane bagasse from making sugar. they have this waste residue. Most of it sits there rotting and been there. I've seen it, Occasionally they burn it to make electricity if the price of electricity is right. You go to Africa. I sat in a very fascinating couple of day meetings with Mars, the Mars company, that is not the planet, and talking about chocolate and cocoa pods, 20 million tons a year in the Ivory Coast. The cocoa pods, they put them down, they chop them up with a machete, comes the bean, the rest of it's left to rot. What a waste. I'm not saying it's environmentally harmful, that's probably not very good, but the waste of resource, the molecules in there, the carbon source is fabulous. We have this amazing availability of raw materials, food waste, food supply chain waste, agricultural waste, etc., that can give us everything we need. This is exactly the same as I showed you before from petrochemicals, but now it's biomass or bio-based chemicals. It's amazing. And we can make all these things really nicely, especially we can make chemicals. And we can also make, oops, sorry, I'll go back. And we can also make some of the things I'll talk a bit more about now, just examples of plastics and solvents. But the point is we can make, I can't think of virtually anything organic, certainly, which is most chemicals are organic. Can't think of almost anything you can't make from biomass. So why not? Let's move in that direction. Now, at the very beginning of biomass, so when you first see an orange, I've got an orange, which is one of my props, and this orange, lovely thing. So of course it's food. Of course it's food. How much of this do you eat? Well, unless you're very strange, I imagine it's less than half, which is the juice. But this is actually a chemical. Oh, it's amazing. It's a fantastic collection of chemicals. And just scratching the surface here, I can smell it. Oh, that's interesting. We'll talk about that chemical in a moment. It's an amazing resource. And on the very surface, just scratching the surface, are what we call waxes. The surface of every plant on the planet, next time you pass a leaf, feel the surface. My wife gets very upset sometimes. I go around feeling the leaves in different places, but that's where the chemicals are, very high concentrations of chemicals, and they are basically natural waxes. So, for example, the Middle East. So the Middle East might be the only place, or one of the very few places on the planet where the amount of biomass would seem to be quite low, except for date palm. They grow millions of date palm trees in the Middle East. And I spent time in the Oman, for example, where looking at their date palm, and date palm has an incredibly high concentration of surface waxes. About 6% by weight of the plant is surface waxes. It's there for reasons. Of course, it's there to preserve, maintain water, to trap water, keep it there, but also insect repellents, insect attractants. It carries out various functions. You can extract those waxes really easily using green chemical methods, green solvents. And they can be used for cosmetics, which they are doing in some cases. They can be used for food aids, food support, food additives. They can be used for various things like, for example, insect semiochemicals. As I mentioned before, nature uses waxes for insect repellent sometimes. So funnily enough, we can also use it as well. There's a whole bunch of things you can make just on this from the surface of the actual plant itself. Once you go below the surface into the orange, for example, then it gets even more interesting. So we start now looking at what's in that orange, apart from the juice that you like to drink. And the answer is lots. You've got limonene, which I'll come back to in a moment. It's a brilliant solvent. Flavonoids, which are very powerful agents used in, for example, cosmetics. Pectin, great for food thickening and also cosmetics as well. And sugars that can be fermented into all sorts of different things like bioethanol or different chemical products as well. What a fantastic resource this orange is. So, as you heard before, I spent some time in the orange farms of Brazil. Half the world's orange juice comes from Brazil. And I went to a farm which had 10 million orange trees, 10 million orange trees in one farm. It was phenomenal. And asked them, okay, they grow all the year round, by the way, different varieties. So they're producing oranges all the time. Huge labor intensity of people picking the oranges, basically. And I said to them, okay, you squeeze them to make orange juice, and you see the tankers going off with orange juice. What happens to the rest of the orange? And they said, somebody comes and takes it away, and we pay them, or if you're lucky, they might not charge you. It's basically a waste. They don't want it. They talk about animal feed, but animals don't want to eat orange. Too bitter, they don't like that. So it's a terrible waste. The potential with oranges, among many, many other things, is enormous, We could do so much more. And the numbers are, it says 31 million tons there. I'm sure it's more than that in reality. Add the lemons, add the satsuma, add all the other citrus fruits around, it gets close to 100 million tons a year of citrus we grow. Each of those items contains interesting chemicals we could exploit. The microwave, by the way, is just one technology we use. So low energy technologies, microwaves are really efficient, not just in your kitchen, but also for processing things as well, like biomass. It'll turn biomass into chemicals remarkably efficiently. One more example, I'll give you a couple of examples now in terms of natural products and their conversion into interesting products. So I think you heard briefly mentioned before pineapples. I work with a company or talk to a company quite a lot in Singapore quite recently, and they are working with pineapple farmers, pineapple growers, to take the leaves, not the pineapple itself, but actually the leaves that are just rotting in the field or burned into fibers. And nowadays they are making some very nice clothing products using these pineapple fibers. The point is, it's one of many examples which is happening more and more. The clothing industry, by the way, I won't have much time to talk about that. I did bring a hat. And I brought the hat because it's a nice example of both the problem and the opportunity. The problem is this hat says it contains linen, viscose, polyester, and cotton. There are 4 different materials in here. Now, you think that already sounds quite complicated. Every one of those will have been processed. Every one of them will contain additives in terms of different chemicals. So what it doesn't tell you here is all the additives, the dyes, the stabilizers, possibly some flame retardants, and various other things as well, just added in there. This is a really complicated bunch of chemicals. But trying to actually get value back from it is very difficult unless you start using the right green technologies, as I'll mention in a moment. So the resources are there, but also in the longer term, we'd like to think let's minimize the problem downstream by using more and more natural resources, more and more waste streams to make them in the first place. And as I said, there are more and more companies, not enough yet, I don't think, but some companies anyway, beginning to take advantage of this. This company is called Nixtevo. There are other companies in Europe doing similar things. Let's take waste streams and start using them to make clothing, etc., etc., etc. One more example, something very different, but sort of more close at home in terms of things I've been directly involved with, is using seaweed to make stuff. So seaweed, well, I brought some seaweed. Why I bring seaweed to Orkney? It sounds a bit crazy. But anyway, it's dried up seaweed. Seaweed's fascinating. It's full of chemicals, really interesting, like everything else, of course. And it's processed. There are seaweed companies around the world. I mentioned the one in China. There's some on the west coast of Scotland as well, I believe. We use seaweed to make, and also orange peel as well, to make this stuff, which is called Starbon. It's a black powder, completely safe, by the way, totally non-toxic. And it's got some very interesting physical properties, very good for absorbing things, including, for example, absorbing unpleasant odors. So actually, as you can see here, one of its applications is in a product called pearls made by a UK company called Trio, and they use it to make for ostomy bags to remove the odors. So one small but interesting application by taking a waste stream, in this case seaweed or orange peel, and making something useful from it. Now, I mentioned limonene on the previous slide. Limonene is there. So when I scratch the orange a bit more, I've got a knife. I don't need the knife because actually I can smell the limonene just by scratching the surface, as I'm sure. Yeah, it's nice. Yeah, that's limonene. Or it's actually a mixture of terpenes, but the predominant one is a molecule called limonene. Limonene, to a chemist, is really interesting because nature, on the whole, doesn't make small volatile compounds, apart from obviously carbon dioxide, water, but on the whole, it doesn't. Most of its organic compounds are complicated and oxygenated. This is a hydrocarbon, a very unusual example of a natural hydrocarbon and volatile. And limonene is a really good solvent. So every time there's an oil disaster, far too often, I'm afraid, they use limonene to clean up the oil sands. And what you see is the price of limonene shooting up. It's an example of a solvent. And solvents is one of the 2 biggest uses of chemicals in the world, apart from fuels. I'm not going to mention fuels. Solvents are everywhere. I mean, the volumes are just incredible. 20 billion kilograms a year. That's just in Europe. Every industry you can think of uses solvents, including, by the way, pharmaceutical manufacturing for all sorts of reasons. Paints and coatings, of course, are the biggest users. The point is, this is a massive consumer of petrochemical solvents. And those solvents include things like toluene, which is carcinogenic. It includes things like dichloromethane, which is also carcinogenic. I mean, the solvents that we use today, almost all of them, hydrocarbon-based, and the vast majority we now know are toxic. We shouldn't be using them at all. Therefore, we need things like limonene to replace them. The problem is, how much limonene is there? I said before, there could be maybe 100 million tons of citrus grown around the world. True. But how much of that is juiced? And how much of that limonene is actually used? Not a lot. We did this data just for information. You can see, get some idea. The USA, for example, you can see here. So this is how much limonene they actually make from their oranges and lemons. This is how much they could make if they're juiced properly, which is not much different really. And this is the amount of toluene, just one of those toxic solvents they use in that country every year. So it can only make a small difference. Some places like Brazil, I mentioned before, look, Brazil already makes more limonene than it needs to replace toluene. Does it do it? No, it doesn't even do it. It doesn't do it because it's stupid, because it can't make the connection between different industries. The orange farmers won't talk to chemical companies. We don't do chemistry. We don't talk to chemical companies. What a wasted opportunity. We need much more integration of these different industries working together to make all this work. The point is limonene is not enough, and there's not enough natural solvents around to satisfy the needs for those various industries. We need to make some natural green biosolvents, including one we call styrene. Styrene, I didn't bring any styrene, but it's basically made from this stuff, which is sawdust. So about 10 years ago, I started working with a company in Australia, and the idea was they came from the paper and pulp industry. Now, the paper and pulp industry is a dying industry. You know, people don't use so much paper as they used to. Newspapers, less paper writing. I'm very sad, really. But the resource is still there. And these forests have managed incredibly well. In places like Australia, Tasmania, Northern Europe, USA, the management of the forest is excellent. It's a great resource. Let's use it. The sawdust can be converted into this molecule we call styrene. And that styrene is a fantastic green solvent that can be used for making all sorts of things and replacing all sorts of nasty, dangerous chemicals. Our first pilot plant was made in Tasmania. It's a wonderful part of the world. It's not dissimilar to Orkney, I would suggest. I mean, it's along the opposite end of the world, really. But Tasmania has a paper and pulp industry, or had a paper and pulp industry. And nowadays they have a small chemical industry based on this technology. So that was a nice experience to be in. And now, by the way, it's now being reproduced in Europe as well. So we're building the first manufacturing plant for this solvent in Europe, again, using sawdust. Just the sawdust left lying around on the ground in sawmills, forest, furniture manufacturing companies, paper and pulp mills, the ones that are left, etc. But the biggest user of all chemicals, of course, are plastics, as I mentioned before. Plastics are like, wow, and the volumes are incredible. And we tend to be based around the family over there. These are the classic polyolefins, as they're called, polyethylene, polypropylene, etc., and a few others. And they all come from oil. The problem is, as I said before, the resource is limited. It's not going to last forever. We're utilizing a very valuable resource to make something we often throw away. The volumes you make are unbelievable. It says there 300 million tons. I've heard also 500 million tons. I mean, there's already 9 billion tons of plastic in the environment out there. And most of it, we don't know where it is. Well, we can guess. It's inside us. It's in the food we eat. It's in the rivers. It's in the sea. It's like, whoa, And for the chemist among you, a bit of molecular structures there, very simple molecular structure. The problem is nature doesn't recognize them. They don't recognize these polyolefins, like polyethylene, like polypropylene. They don't know what to do. They can't eat it. Therefore, it hangs around and survives in the environment. So the future, of course, has to be to make new bio-based plastic. Yes, of course. But we have to also deal with what we have, all that huge amount of waste stuff out there. And the problem we have in dealing with it goes back to what I've said before, which is what we've got already is so complicated. There's the hat I've got there. This actually, the plastic bottle isn't too bad, polyethylene, and that is being used already. They're now using plastic bottles to make things like shoes. So you can use the PET this is made from to make, for example, the clothes some of you are wearing. Like it here as well, the polyester here will be based on the new version will be based on a recycled plastic bottle. That sounds pretty good. This is a favorite of mine, a plastic food tray. Oh my God, have you tried to recycle this? Different plastic there, different plastic here, powerful adhesive down the side. Real nightmare to separate. Why do they make it so complicated? Anyway, we are working on it. So the business side of me, working around the green chemistry company Hannibal, is looking at this very hard. We're looking at separation of polymers and the foils and everything else, and we are making progress. It's a very exciting opportunity. We have a company in Ireland we work with, and they do take the base plate, most of this, they recycle that bit, but they can't get this top. So they can't recycle. Covered in adhesive, it can't be recycled again. All that needs is good green chemical technology, like green solvents I've talked about before. Using them the right way, and whoa, you've got a fantastic technology opportunity. One of my Hannibal guys did this. It's lovely, isn't it? It's basically saying there are opportunities. Everything I've talked about is an opportunity. It's a threat, sure, if we leave it alone. It's also a fantastic opportunity. So my company Animal's taking waste streams of all sorts of different types and thinking about them as a resource for the future. And all these things I've talked about end up as waste at the moment. Let's use them as a resource. It can be quite complicated. Don't try to take this all in. The point is, you can separate all these complicated, multi-layered things if you have the patience, of course, but also the right green chemical technology, the right green solvents. So, yes, threats, absolutely, opportunities, definitely. Just a couple of minutes to finish off by just going back to something I can't ignore. I said early on, we are using more and more elements to make more and more stuff, oft for good reasons, maybe, but not in a very clever way. We are running out of metals. The reality is every time we dig a new source of lithium or whatever it is, the quality of the ore goes down, the economic cost of getting it goes up, the waste streams processing it go up. It's bad. The amount of energy we use to process ore is incredible. It's already really high. So where are these minerals? What's left if we carry on using virgin resources to get our future supplies of cobalt, lithium, manganese, etc., etc.? This is where they are. Look, Australia's doing great. South Africa, fantastic. Oh, China, fantastic. Europe, not a lot. We don't have a lot of natural metals in Europe. So really we are in trouble unless we start using. And of course, what it ignores are the landfill sites. You add in the landfill sites there, you'll have huge amounts of metals. The Japanese have realized this, they're working on it. But on the whole, we don't recycle. We don't recycle at the moment. This is another version of the periodic table. The red, we don't recycle at all. What a waste, These are the ones we talked about running out, and we don't recycle what we use already. Down here, the rare earths, they're called for making things like wind turbines and some of the batteries and so on. Elements here as well for batteries. There's lithium. We don't recycle them at the moment, so no wonder we're running out. And actually, let's think again about waste. There are lots of natural waste sources, natural, unnatural waste sources we can start exploiting to get the metals back from. The mining waste, of course, we're very inefficient at the mining. Landfill mining, I mentioned before, why not? We can use landfill mining. Electronic waste, it's huge quantities. And just coming at the back of old-fashioned cars with catalytic converters, the metals are spewing out the back. They're captured, by the way, by the local biomass. People now go down the highways of California, used to anyway, and they harvest the biomass, take the biomass back to a plant, and recover the precious metals that came from the catalytic converters. Cars, great. As I mentioned, the Japanese are ahead of us, as often is the case, and they are actually taking waste streams now from electronic waste. They burn the waste streams and they get the metals back again. And they are now making some interesting data there, like, for example, 3 times more gold, silver, and indium than the world uses in a year, just from the waste, just from burning electronic waste. Very clever. It's not the best way of doing it, but it's better than nothing. I'll leave you with one green chemical technology that could also be used. Star bonds I mentioned before, by the way, they could also be used to capture metals, which is very nice. But actually, the other one I want to mention is something called phytoremediation or phytoextraction, because plants can also capture metals. After Chernobyl, the awful disaster there, within months of post-Chernobyl, they found plants growing very close to the disaster zone. Plants are incredibly robust creatures. They will pick up the metals and somehow adjust their physiology to cope with them. Well, sometimes it kills them, actually. So we can use plants to capture metals from waste streams. It's a very effective way of concentrating metals and then taking the plant afterwards, making it part of a biorefinery, getting the metals out, getting the carbon value back, etc., etc. Hardly done at all now. It is being talked about at least. Great. Okay, well, I've covered lots of area. I know to my time limit, so I'll just finish by showing my sort of acknowledgement slide. It all came out the Green Chemistry Centre at York, and this is an old picture, but it's still representative. People from 20 plus different countries working together, from MSc, PhD, senior scientists, research, all sorts of people. The New York company now down here, these are the Irish labs, and a nice bunch of people there working together to try and just talk about and to do clever research and publish papers, but really make it happen in a real world. We try and get this across in all sorts of ways, like outreach. I brought some examples of these magazines. It's now been taken over by collaborating universities, but we started it at York. It's all about making this available to younger children. These are for young children. These magazines are so popular, they're being translated to French, and then I've been translated into Chinese. And my very, very, very last slide, which comes from one of those bright young things I showed you before in the top picture. And I said to them, okay, they were very good artists. I said, okay, can you represented cartoon form what this all means? So there we are. That's where we were. the dirty, polluting industry, pollution coming out the chimney, going into the river. The local vegetation was all dead. You wouldn't dare live near the place. This is the way it was, and it still is, sadly, in some places. It was like this, by the way, 20 years ago in the UK. I went to sites like this. Now it's much, much better, mostly much, much better. But there are still places in the world like this. Anyway, what should it be like in the future? What's the green chemistry message telling us? Well, interesting. The factory's got no chimney. There's no pollution. There's nothing going into the rivers. People can live close by because it's safe now. It's not no risk of explosion. It's all been done the right way. We're growing the local resource. The sun's come out because it's all nice. And if you look very carefully, the flower is smiling because chemistry's gone back to where it started, which is all part of the environment. Thank you very much.
Thank you very much, James. That's an extremely thought-provoking presentation. I've certainly provoked thoughts in myself. We've got two roving mics, Lorna and Kaelin. So if you put your hands up, they will get to you and you can ask your questions. There's also Slido is still on the go, so if people want to submit questions by Slido, please do. So before someone asks something, I shall ask you something, James. See, prior to the routine use of petrochemicals to make, for example, fibres for clothing, right, can we learn off the pre-petrochemical times, but use improved technologies and techniques to make, for example, natural fibres better, more efficient, less waste?
I think so. I think, yes, you're right. We are, in a way, going back to where we were in terms of the raw materials, yes. But the way we handle them, of course. I'm not saying chemistry's bad. I shouldn't say that, It's all about applying it the right way, an efficient way, a clean, safe way. Yes, we've learned a lot in the last 100 years. I think the petrochemical industry is an amazing example of efficiency. I mentioned that before. It's trying to be efficient. And the range of things it can make is fabulous. Well, yeah, just drinking water. So let's learn from that, but apply that into a more sustainable raw material base as they had 200 years ago. Of course, the demand these days is so much higher than it was. And then, of course, it was very localized, whereas nowadays we talk about these global industries, making huge quantities of stuff. So it's different logistics, and that the logistics can be a bit of a nightmare because it's like, if you say to a big German company like BASF, you say, why don't you, transpose your chemical production into Africa and use the local resources? They'll say, this costs us €1 trillion. I mean, the investment is staggering. So it's going to be really expensive. You can't just do it overnight. But yes, what you're fundamentally saying is, yes, absolutely, that's what we should do. Yes.
Okay. Any questions from the audience?
Is that on?
Yes.
Thank you. James, thank you very much indeed. Really interesting talk. I wonder if you could direct us to any decent definitive sources of some of these impacts, because quite often you hear competing claims such as hemp is more efficient than cotton for water and various bits and pieces. And one of the challenges when we're trying to do things ourselves is knowing, frankly, who to believe. And I'm just wondering if you've come across any good examples, because I've not seen the information presented in such a clear way as you did with those periodic tables. I'm just wondering if there's anything else you could direct us to.
Oh, gosh. I wish the answer was yes. I mean, it's getting better in terms of spotting the problems, if you see what I mean. So we're getting quite good at actually measuring toxicity. So, 10 years ago, we knew nothing about the toxicity of most chemicals. Now we do. So that's better. So I think we're better at identifying the problem area. But where you talk about, the opportunity side and the relative merits of using different raw materials, the trouble is, I mean, just taking any raw material like an orange or whatever to make stuff, it takes effort to really work it all out. And so people talk about life cycle assessment, of course, is a big thing. And even that's a variable feast. I mean, it varies depending on the data you put in, and it could change from week to week. So I'm asked that question or variations on that question a lot. And I kind of cop out by saying that you give us loads I can point you to read, but the trouble is it'll be out of date by next year, or by the time you read it even. because, people's ability to maximize the chemical efficiency, say, of a raw material is improving, as it should be. And also, still read a lot of supposedly very high quality science papers that ignore critical things, like they forget for example, I'm doing a lot of reading for various reasons about rubber recycling end of life tires. There are so many old tires now. You can see them from space. It's amazing. We've got tire mountains. We've got old clothing mountains as well, by the way, in the Chilean desert. You can see from space. Um, if you look at rubber, rubber's a really complicated thing in terms of the different chemicals in there. And we're trying to think about, sort of alternative ways of, whatever. And the trouble is, people are now looking at the raw material and thinking, let's make that better. Or they're thinking about the end of life, especially, let's recycle better. All very good, but they forget the bit in the middle, the chemistry, which itself is hugely environmentally impactful. So the trouble is that there's very little comprehensive data done on these situations. Even oranges, we've tried, but I'm sure we're missing things there. And even when we did that, it didn't, I'm afraid, didn't persuade the Brazilian orange farmers to. I mean, often it comes down to socioeconomic factors as much as anything, or just psychology of just saying, why don't you? Another off the wall example, one more is I mentioned sawdust. So people now say we are now being sustainable in our electricity production by burning biomass. So Drax Power Station, not far from where I live in North Yorkshire, Drax Power Station it's the largest electricity plant in Europe. And they are now burning biomass, like 20 million tons a year of biomass to make electricity. Is that better than burning coal? Possibly, but think about where it comes from. It's actually been shipped from halfway around the world. There is quite a lot of processing goes into it. They still have lots of residues left at the end. I don't see them doing proper calculations. So I know Greenpeace challenged them. I know they've just been fined by the government, 50 million or something, by not doing the calculations properly. So the data is, even when the data is there, people are not using it well. So I can try to answer a specific if you want to email me or something, and try and point you. But I mean, as a generalization, are people? No. The data probably is there if you look hard enough, but then of course you might worry about. So I'm sorry, I'm going around your question, but the essential answer is not really, unless you want to identify the problems, because we are better at identifying those.
Okay. I've got one last question, which has come in on Slido. You talked about oranges, but what high wax waste is potentially common in Scotland?
What is the high wax?
High wax?
I see. Oh, God, any plants. Any plant contains waxes. I mean, even basic cereal straw has about 1 to 2% wax. So, gosh, I mean, I'll tell you a story. We actually, as Katrina knows, about 10 years ago, we almost set up a biorefinery in near Inverness, encouraged by the Hounds and Hounds Enterprise Board. Sadly, the financial crash diverted the money elsewhere. But we looked there and we saw, well, actually, trees are a fabulous resource, as I mentioned before, and the straws, cereal straws. So cereal straws, in terms of volume, because you need lots to make it practical. So I would suggest cereal straws are probably the best.
Thank you once again, and can we just thank the speaker in the normal way? Thank you.